Today, we begin with the basic Solow model, a simple framework, but one that changed how economists think about growth. Before writing down the model, let us begin with two patterns. First, an economy may grow quickly when it starts with little capital. However, as it accumulates more and more capital, the same extra investment adds less and less. Second, countries do not all begin at the same level. A poor economy may grow faster, not because it is magically better, but because it is further away from its long-run position. Therefore, the Solow growth model starts from two questions. Why does growth slow down, and when should we expect catch-up? To explain these patterns, Solow starts from a neoclassical production function. The first and most important assumption is diminishing marginal returns. If we increase capital or labor, output rises, but it does not rise at the same speed forever. When an input is scarce, one extra unit is very productive. When that input is already abundant, one extra unit adds much less. This is the key force behind growth slowdown. The second assumption is constant returns to scale. If we double both capital and labor, output also doubles. This assumption let us divide everything by labor and study the economy in per worker terms. So, instead of tracking total output and total capital, we can focus on a simpler relationship. Output per worker as a function of capital per worker. Finally, the another condition describes the extreme cases. When an input is almost absent, its marginal product is very high. When it is extremely abundant, its marginal product approaches zero. It is to ensure an interior solution. Now, we need to describe how capital changes over time. Capital is a stock. It helps produce output today, and if part of that output is saved and invested, it builds capital and output for tomorrow. In the basic Solow model, we usually begin with a closed economy without government, so saving becomes investment. This means investment is the inflow into the capital stock. But capital also wears out. Machines break down, buildings age, and existing capital depreciates. So, net capital accumulation is simply the inflow minus the outflow. Capital rises through investment and falls through depreciation. Since investment equals saving, and saving is a constant fraction of output, we can write the aggregate capital accumulation as saving minus depreciation. However, the Solow growth model is not mainly about the total capital. It is more about capital per worker. So, we divide by labor and move to per worker variables. Investment per worker is SF, but capital per worker is also diluted by depreciation and population growth. That gives us the central equation of the basic Solow growth model. Capital per worker changes according to investment per worker minus break-even investment. Now that we have the equation, and we can turn it into a diagram. On the horizontal axis, put capital per worker, K. On the vertical axis, we can read output, investment, and break-even investment per worker. First, output per worker is Y. It rises with K, but because of diminishing marginal returns, it becomes flatter and flatter. Second, saving turns a constant fraction of output into investment. So, investment per worker is SF. This curve has the same basic shape as output, but it lies below output. Third, break-even investment is delta plus N times K. It is the amount of investment needed just to keep capital per worker constant. When investment equals break-even investment, capital per worker no longer changes. And this point is what we call the steady state. To the left of K star, investment is larger than break-even investment, so capital per worker rises. And this is the visual heart of the Solow growth model. The previous diagram showed the steady state, but now we want to see the direction of motion. Start from the capital accumulation equation and divide both sides by K. Then the growth rate of capital per worker is investment per unit of capital minus the break-even rate. So the phase diagram compares two rates. The green curve is the investment per unit of capital. When K is very small, capital is scarce, so one more unit of capital is very productive. That is why the curve is high on the left. When K is very large, capital is already abundant, so each unit of capital earns less. That is why the curve slopes downward. Now, we add the break-even rate, N plus delta. This is constant, because it is the rate needed to offset depreciation and population growth. At the intersection, investment per unit of capital exactly equals the break-even rate. So, the growth rate of capital per worker equals 0, and this is the steady state, K star. To the left of K star, the green curve is above the break-even line. So, the growth rate of capital per worker is greater than 0, and capital per worker rises. To the right of K star, the green curve is below the break-even line. So the growth rate of capital per worker is smaller than 0, and capital per worker falls back. This is why the steady state is stable. Growth is fast when capital is scarce, but it slows down as the economy approaches K star. Let's proceed to the question of catch-up. When should a poor economy grow faster than a richer economy? The simplest case is absolute convergence. This means two economies have exactly the same structural parameters, same saving rate, same population growth, same depreciation, and the same production technology. Then, they face the exactly same phase diagram, and therefore the same steady state, K star. Suppose the poorer economy starts further below K star. Its gap between the investment and break-even investment is larger. So, its growth rate is higher during transition. And that is the Solow logic behind catch-up. But this result is not automatic. Because countries may differ in their saving rates, population growth, institutions, or production structure, then they do not necessarily share the same steady state. For example, a higher saving rate shifts the investment curve upward, and that raises the steady state level of capital per worker. So, a country grows faster when it is further below its own steady state, not simply because it is poorer than another country. And this is the conditional convergence. In fact, economies can all converge, but converge to different long-run levels. So, Solow does not say every poor country automatically catches up. It says catch-up depends on the steady state that the economy is moving toward. So far, the Solow growth model explains transition and catch-up. But there's a limit to the story. Once the economy reaches a steady state, capital per worker stops changing. And if technology is fixed, output per worker also stops growing. However, in the real world, capital per worker has kept rising for decades since the Industrial Revolution. So, Solow needs one more force, and the missing ingredient is technological progress, represented by A. This is the bridge from the basic Solow growth model to the Solow growth model with technological progress. Now, Solow adds technology into the production function. Previously, output depended only on capital and labor. But now, we multiply the production function by A. Here, A measures the level of technology. A higher A means the same capital and labor can produce more output. So, technology does not just move us along the curve. It shifts the entire production function upward. And with constant returns to scale, we can again divide by labor. And this gives output per worker, as technology times output per worker from capital alone. So even if K stops rising, output per worker can still rise if K keeps growing. And that is how Solow restores sustained growth in output per worker. Let's put technology back into the Solow diagram. Without technological progress, investment per worker is SF. But with technology, output per worker becomes AF. So, investment per worker becomes SAF. When A rises, the investment curve shifts upward, and the break-even line does not move. Depreciation and population are still the same forces. So, the intersection moves to the right. A higher technology level supports a higher capital stock per worker. If technology rises again, the curve shifts upward again. The economy is not just moving toward one fixed target anymore. It is chasing a moving target created by technological progress. And this is why technology can keep the growth process alive. So, Solow has now restored sustained growth. But there's one final problem. The model assumes that technology grows at a constant rate, G. This gives the economy a source of long-run growth. But the model does not explain why A grows. Technological progress is treated as a black box. So, Solow explains how technology can sustain growth, but not why technological progress occurs. And that is why this is called an exogenous growth model. Exogenous means the key growth force comes from outside the model. Later growth theory asks a deeper question. Can the growth of A be explained inside the model? Paul Rummer answered this question through innovation and R&D process, and Robert Lucas answered this through human capital accumulation. So, Solow is not the end of growth theory. It is the starting point for asking where long-run growth really comes from.